So in our last section for Chapter 3, we're going to be talking about some advanced counting methods with things called permutations and combinations, and understand that these things all come directly from the fundamental counting principle, just with a bit of added direction. So to get the flavor of what we're working on, let's start with an example where we'll say that you are going to a race. Now, you're not going to run in the race, but you're going to spectate. You've got 8 runners there, and you want to pick who's going to come in first for no good reason, because gambling's not legal in Florida. Not yet, anyway. At least not that kind of gambling. But the point is, you want to see who's going to come in first. You want to make a guess for it, because it'll make it more interesting for you if you've got someone to cheer for. You might not know any of the runners. Well, if you want to figure out who's going to come in first, you have 8 options, because you've got 8 runners. But let's say you want to make it more interesting for yourself. And let's say you want to find out, okay, we'll say who's going to come in first. What about second? Well, if you want to find out who's going to come in second, they can't also come in first. So whoever came in first is out of the picture. That means you've got 7 left for second. And then from second, you say, okay, well, what about third? Well, first and second can't also be third, otherwise third would have a really bad day. So we've only got 6 options left then for third. And then if we wanted to get fourth, we have 5, then 4, then 3, then 2, then 1. So if we wanted the total options, the total number of ways that we could select the order for the racers, I mean, see who came in what position, we get that by the fundamental counting principle. Because you've got 8 for the first, 7 for the second, 6 for the third, and so on, you just multiply them out. That's what the fundamental counting principle says, is if you want the total number of options, you multiply the number of options for each case. But let's say that instead, for whatever reason, you also want to think about who might come in the top 3. Well, for the top 3, it's really just these guys up here. Because you've got 8 for the first, 7 for the second, and 6 for the third. And if you wanted a number to attach to these, because, hey, people like numbers, I guess, I don't know. And so, this isn't a math class, right? We would see that for the full 8, even though I'm going to be leaning onto the next page, we would have 40,320 options, while for top 3, we'd only have 336. Still quite a lot, but a little bit less. Where this wasn't so bad for 8 things, it wasn't so bad for 3 things, but in general, if we have more options, this is going to get clunkier. Like if we want to talk about the Boston Marathon, or some other race that has much more than 8 runners in it, trying to describe all of the options might take a little while longer to put out longhand. And as a result, we have a shorthand notation for this. We have a nice way of condensing down this notation, where we say that this value here is equal to 8 factorial. So it's 8 with an exclamation point. That doesn't mean that 8 is incredibly happy to be here. That means we are taking 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We are multiplying out all of the numbers below 8. And in general, we have what's called n factorial for n options. Where again, n factorial doesn't mean n is very happy. It means we've got this n, and we're going to multiply it by n minus 1, and n minus 2, and n minus 3, and n minus 4, and n minus 5, all the way down to 3, 2, and 1 until we run out of smaller natural numbers to multiply in there. Where we can think of this as representing the total number of ways that you can arrange n objects where order matters, and we're going to talk about every single one of them without any repeats. Where there's one very important special case for this. We say that 0 factorial is equal to 1. And there's two explanations for it. One is simple mathematical convenience, that there are some formulas we're going to see in conjunction to that type of construction where they wouldn't work if 0 factorial was anything other than 1. But also, if we're thinking about n factorial as a total arrangement of n things without repeats, we can think of 0 factorial as the number of ways to arrange nothing, which is trivially one way. You got nothing, it is nothing, it stayed nothing, but I guess you did something? Anyway, the idea here is that 0 factorial is 1. That's a value that we have to just take. Where looking at these ideas for that sort of construction, we can take this idea of factorials and generalize it to a thing called permutations, where we could say that this is 8 permute 3, where in general a permutation specifically, and I'm going to erase this part here because it's going to get in the way, of R objects from N is denoted NPR, and no, that's not National Public Radio, where this value is going to be n factorial over n minus r factorial. And there's other ways you can denote this. I've seen permutations also denoted P n comma r in parentheses. I think this notation's a bit cleaner, but this is the one the book uses, so I'll try to use it as much as possible. Where what this does is it looks at selections of R from N with respect to order, that is, order matters, and no repeats. That is, once you pull something, it doesn't go back in the bag, it's taken as an option, like with that race. You can't have someone be first and second and third, otherwise, well, they'd be hogging all the medals, and what's the point of having the race then? But for this, what you can think of the permutations as doing is saying, okay, I've got n options. If I want to find all the ways I can arrange n of them, I just multiply everything out. I say, I don't care, let's just spit it all out there. But then I say, well, I don't care about all of them. And like with the race, I'm sure who comes in fourth will be very offended by this, but really we want to know who medaled. We want to know top 3. And to get that top 3, we can think about all of our options and then say, well, the 8 minus 3 of them, the other 5, don't really matter. So mathematically, we take out those 5 sets of arrangements that don't matter by dividing them away. And the reason why this works is because we get some very special things that go on with these permutations algebraically. So looking at this idea right here, that 8 permute 3, what we have there, using the formula now, is 8 factorial over 8 minus 3 factorial, where we write this as 8 factorial over 5 factorial, and then something special happens with these factorials. That we're not going to bother that 5 factorial for now. It's doing its best. We're not going to make things harder. But on top, we can pull out a 7 factorial, get 8 times 7 factorial over 5 factorial, and say, great, we did nothing. But, well, it's a little longer. And then we can do this again. 8 times 7 times 6 factorial over 5 factorial. And hopefully some of you are seeing the pattern we're going to be getting towards here. Because if we do this a third time, we would have 8 times 7 times 6 times 5 factorial over 5 factorial. And there, now we have something that cancels. Those 5 factorials go away, and we're left with 8 times 7 times 6, like before. We took all of our options and counted down the ones that don't matter and kicked them out. Where when it comes to permutations and factorials, there's one really important thing that you should understand. In general, if we're talking about something like, let's say, 2 times 4 factorial, this is a very different value from 2 times 4 quantity factorial. And in general, this value is considerably larger. There are a couple of special cases where they're equal, but usually this is a much bigger thing. So be very careful about how factorials are arranged when you're looking at multiplying them or canceling them, and don't stick them together until you know that that's all that's left. It's very easy to turn something that doesn't have a large number of options into a thing with a considerably more ungainly amount of options when it comes to factorials. And next, we're going to get a really quick example seeing how we can use this. Well, another one.